Hello, lovely people. How is everyone doing today? Rarely see. Oh no, I'm sorry, Analog. Also, sorry y'all that I am running so late today. I was tweaking my PowerPoint and then I just kept tweaking it. Which I definitely should have stopped doing sooner, but I didn't, and now we're here. So, at least I made it. You know, that should count for something, right? So how's everybody doing? We are doing more computery things today, which is always fun. Specifically today, we are going to be talking about subtleties of IP addressing, as well as some routing algorithms for navigating the net, and kind of why we needed to come up with new routing algorithms and new methods of IP addressing. I'm wearing headphones still. Let's take those off. You just have a non-optimal routing table that took the long way here. The routing table of my brain. I don't even think I can make that one make sense. We'll just have to leave it as a nonsensical statement. By yours truly. Yeah, I had a really nice weekend. Got to hang out with some friends. They are D8 earrings. They were a gift. They were a gift by a friend of mine. Thank you. Yeah, they're pretty easy to make. You have to have something that can, like, drill a hole, but once you have that, you're good to go. Optimizing a routing table is very difficult, especially when Nmap, using Nmap is a federal computer crime. Thankfully, it has yet to be enforced as a federal computer crime in the United States, and in fact, it has previously been said in court that Nmap doesn't count as, like, actually trying to penetrate something, because you're not. You're just looking at it from the outside. You are gathering the information that is publicly available about it. One day you'll get your ears pierced and have much cooler earrings. You can also get the earring modification thing. They make these little converters that convert normal earrings into dangly earrings, which you could check out as well if you aren't wanting to get your ears pierced. If you are, then more power to you. Go to a proper place. Don't go to Claire's like the rest of us did. Oh, God. I wish I had known to insist on going to a proper body piercer. Did they hollow them out? No, they are standard weight D8s. Hollowing them out would have been nice, but they're not too heavy. These ones are a pretty light plastic, so D20s I find are too heavy for my ears to be comfortable, but I don't tend to have much of a problem with D8s and smallers. On the fence because the piercing frame maintenance seems like a lot of work. To be fair, it's been a long time since I remember, since I had to do this. Since I had to do my ears. Wow, brain just like, bleh. Did not want to function there for a minute. It's been Shogun, only on Hulu. Oh dear, I lost my OBS. There we go. It's been a long time since I've had to do piercing maintenance, really, because I got these piercings, when I got these piercings 13 years ago. And I'd say that they were kind of, one of my ears, because I went to Claire's, got pierced sideways a little bit. And that ear took about 2 or 3 years to like properly heal up. But nowadays, I don't really have to do much of anything to them. You wish that Claire's et al. Weren't allowed to sell piercing services. They're incompetent at best and cause serious damage with their shoddy equipment. Yeah. Also, downside of going to Claire's is also it's way more stressful because you go and typically there's like a screaming 1 or 2-year-old who is getting their ears pierced right before you. This has happened to me. This happened to my sister. This happened to all of the people in my family I know of who got their ears pierced. Person who went before us was a screaming child who, in fact, started screaming more after their ears got pierced. Because it does hurt. It doesn't hurt like an insurmountable amount. But if you're a baby and it's the first time you've ever experienced that sort of pain, it's not a fun time and makes the entire experience way more stressful. Proper tattooing place. Yep, 100%. My kettle just went off, so I'm gonna go grab my tea, and then we're gonna start the session for today. Whoop, whoop. Oh dear, I just spilled on myself. That's fine. It's not. I mean, it is 212 degrees, but it only splashed a little bit. That's fine. Tea of the day is boring old Tetley. Oh yeah, always. This is my teapot. I love it very much. I drink 1 to 2 pots of tea a day. Not all caffeinated. But yeah, this is my main teapot. It is about the size that I need to get through a day, so. Alrighty, let's get started, my friends. Routing revelations and explorations is the theme of this week, starting with subtleties of IP addressing and algorithms for navigating the net. So, we're going to start with a review of last lesson. So last week we were talking about the OSI model, which is the network stack. Then we're going to talk about review TCP versus UDP, the main characteristic differences there. And then we'll go on to talking about IPv4, the sorts of addressing that IPv4 was used for, and why that happened, why there were changes. And then we're going to get into talking about routing. Today is going to be kind of an overview of routing and major kinds of routing. Again, I think that it's important to think about this in terms of the history of how we evolved to get here. And we'll go more into that in the routing section, but specifically, like, we started with static routing. We started with routing tables that were hand coded, right? And then, as all good programmers do, as all good programmers are lazy, it's one of the 5 qualities of a good programmer. Sysadmins wanted to be able to automate the process of creating those routing tables, and started inventing new routing methods, new routing algorithms that could automatically determine where to send messages. And yeah, we'll go into that towards the end of the lesson. So, first up, Calypso is a good cat nun. Thank you. So first up, review of the OSI model. As you remember from last time, we have this lovely little mnemonic to help us remember it. Please do not tell the secret password to anyone, which stands for physical, data link, network, transport, session, presentation, and application. All 7 layers of the network stack, the OSI model. So, thank you for the follower. Thank you for the follow. I hope you enjoy your time and stay in the Eclectic Library. Alrighty. Yeah, so first up, we've got the physical layer. The physical layer is responsible for activating, maintaining, and deactivating the physical links between the network devices. So this is literally Ethernet cable plugged into your computer, plugged into the router. This is the fiber optic cable that is running to your house if you have fiber. This is the physical components that make up the network. The actual, literal, physical devices that electrical engineers have worked on to create. For debugging the physical layer, things you're going to want to check are, is the device unplugged? Does it have power? Are there damaged connectors? Are there damaged cables? That kind of thing. Thanks! I got it from somewhere else. I don't remember where, but I will find out. Next up, we went over the data link layer. Summary of the information surrounding the data link layer is the data link layer is responsible for formatting the data for transmission over the physical wires. It is also responsible for controlling the rate of the data flow within the network. So it's responsible for actually deciding when the next message gets pushed. It is responsible for tracking which devices are connected to the network. So that's keeping track of all of the various MAC addresses. And it is responsible for deciding what to do if a message has been corrupted during transit. So if some bits have gotten switched off and on when they weren't supposed to. For debugging the data link layer, you're going to check the lower layers first. So you're going to check the physical layer. And then you're probably going to check things like, are there 2 nodes that are trying to talk to each other that are failing to connect? Or is their connection dropping intermittently? Or are you seeing an abnormally large number of transmission errors? Those are the sorts of problems that you're going to run into in the data link layer. Chugging right along to the network layer. The network layer is responsible for sending information via routers. So no longer are we handling sending information from device to device. We're talking about sending things from network to network. The network layer in combination with the data link layer is responsible for tracking which devices are connected to the network. So how to convert the IP address into a MAC address, where the MAC address is the decided at point of manufacturing address for every single device. Every single device has a unique MAC address. Your phone, your computer, your etc. And that unique MAC address maps to an IP address if your device is connected to a network. So, network layer combined with data link layer are responsible for doing that conversion. Finally, the network layer is also responsible for keeping track of available paths to other networks. And it does that via something called a routing table, which we'll be talking about more today and tomorrow. For debugging at the network layer, you are, as always, going to check the lower layers first. Then you're probably going to check, is the IP address incorrectly configured? Or is there a bad router? Or is the routing table misconfigured? That kind of thing. Alrighty, how we doing so far? I know we just blew through all of the more physically layers of stuff. How are you feeling? Any questions? Any comments? Any concerns? Hearing none. Chugging right along onto the transport layer. So transport layer is responsible for handling for deciding the method. The transport layer is responsible for deciding the method of connection between two nodes. So whether or not you're using TCP or UDP as your method of connection, of communication. Keep in mind, and we're going to be going into this in more detail very, very shortly, but TCP is a communication method that emphasizes quality of data. It is centered around having a solid connection between the two nodes that are talking. UDP emphasizes speed. So it is a connectionless communication. You're just throwing things out into the void and hoping that they arrive at the place that you're addressing them to. The transport layer is also responsible for deciding how the data packets are going to be broken up and sent over the network. Now, at a lower level, at that data link level, they might be chopped up into even smaller pieces, but at the transport level, what's being decided is this is one cohesive packet. This is what I am logically considering to be one unit of data. That's what's being decided at the transport level. I know that's a bit of a funky distinction, so please feel free to ask any questions if that didn't click for you. But yeah, that's what the transport layer is responsible for. It's responsible for deciding, do I care about speed more, or do I care about quality of data more? If so, pick a different protocol. And it's responsible for deciding the logical unit size for one data packet. For debugging at the transport layer, you are, again, gonna check the lower layers first. Then you're probably going to check, hey, is there a firewall or an access control list that is blocking port access? Either something on my end, on the source node's end saying, hey, you can't send out TCP through that port, or you can't send out UDP through that port. Or on the destination end saying, hey, I'm not accepting TCP requests from that address. Hey, I'm not accepting UDP requests from that address. So that's method number one. Next thing you're probably going to check if you're having an issue at the transport layer, which I have apparently put twice, are there quality of service settings on the source router, on the source node's router that are misconfigured, or are there quality of service settings on the destination node's router that are misconfigured? A quality of service setting is something that some routers have, which allows you, for your own individual private local area network, to configure prioritization for different messages. For example, if you care a lot about making sure that you have minimal interruptions to your Netflix experience, but you also want to be downloading something from BitTorrent, you could set on your router a quality of service setting which prioritizes above anything else messages, incoming packets from Netflix. It says, hey, if it's a Netflix IP address, send it to the front of the queue. Make sure that it gets sent to the computers within my network first, before anything else. And you might say, hey, BitTorrent, I don't really care how long it takes that to download, so it can get pushed to the back of the queue as many times as it needs to. What can happen then, though, if you have this set up poorly, is if you're constantly streaming Netflix and you're constantly getting new Netflix packets, those BitTorrent packets are never going to be processed. They're never going to get brought into your network and sent to the appropriate computer. So at the transport layer, this is a problem you can run into if there is a poor configuration of a quality of service setting on a destination router. Analog says, close your ports. Yes, please close your ports. Remember that if your computer is sitting and visible on a public network, anybody can see it. Anybody can send messages to it. Anybody could say, hey, I am sending something to you via UDP. Take it. And if you don't have your ports properly configured, you might take it. Less of an issue with. We will talk more about specific reasons why that can go very poorly for you as we continue this lesson. Yeah, and it might be malware. It could be something that's going to install something bad on your computer, or that's going to sit in, whether that's like actively taking over control of your computer, opening up terminals on your computer where the person sitting on the other machine that's accessing yours can do whatever they want. For example, if they're able to access your telnet port. Again, we'll go over what the various standard ports are at a later point in time. But yeah, you don't want to have open ports sitting just open for anybody on the internet to chuck stuff into. You never know which one of them is going to be a bomb. Or spyware. Yeah. Next up, we've got the session layer. Which handles establishing, maintaining, and terminating sessions between two specific end-user applications. So, whereas the data link layer was concerned about individual devices being able to talk to each other, and the network layer was concerned with, now taking a step up, we're no longer dealing with individual devices, but we're now dealing with communicating from network to network. At the session layer, what you're talking about is a step up from even that. It's, hey, this individual user program running on this machine over here wants to talk to this individual user program running on that machine over there. So even more abstracted from the hardware. So debugging tips for the session layer. As always, you're going to check the lower layers first. Then you're going to check, hey, is the application I'm expecting to be talking to on that other machine, is it actually reachable? Is it up and running? Is that server available? If it is available, if it's sitting up there, is it maybe incorrectly configured, or is my application maybe incorrectly configured and not allowing me to send messages out? Or has my connection timed out? Maybe I've been sitting here too long and I need to reestablish a session. I need to start a new session so that we can start talking again. A reason that sessions will often time out is for security reasons. You don't necessarily want your bank to allow an open connection between your computer and your bank servers for infinite amounts of time. So if your bank isn't getting messages from you, from your client, from the client machine, from your machine, Its servers are probably going to close that connection after about 10 to 15 minutes, just for good cybersecurity reasons. Because you might have walked away from your computer and somebody else might have walked over. You never know. Oh, I never changed our listed activity for the day. Whoops. Alrighty. Oops. Let's update that slide. Okay. Presentation layer is next. And this is what handles kind of two separate tasks. It handles character encoding and decoding. So if your computer is, what's an example? Like if your program is displaying, is interpreting characters using ASCII versus if it's interpreting characters using Unicode. And it's also responsible for encryption and data formatting. So this is where like any cryptography stuff that we've talked about so far happens. This is where something gets signed with something gets brain. This is where you're going to do your private key encryption, for example, or unlocking something with your sender's public key, or any other methods of encryption are going to happen here. Debugging tips for the presentation layer. As always, you're going to check your lower levels first. Next up, you're going to check, hey, are there any missing drivers? Is my translation, do I not have the right driver to translate from this device to this device? Are your drivers corrupted? Are they maybe scrambled? Do you need to reinstall your drivers? And does the user actually have correct OS permissions? This is a thing that you can run into here at the presentation layer. Sometimes a particular OS user isn't going to be allowed to encrypt something or allowed to unencrypt something. And sometimes they're not going to have access to certain drivers. For example, if there's a particular user on a device that hasn't been granted access to use the printers, they may not have the ability to talk to the printers at all. And that would need to be granted by your sysadmin. Okay. And last but not least, in the OSI stack, we've got the application layer. The application layer is responsible for handling the services used by end user applications. Note, this is not the applications themselves. The application layer is not the applications themselves. It is the thing that is responsible for handling the network needs of those end user applications. So that's going to be like the HTTP protocol, for example. Debugging tips. As always, we check the lower layers first. Then you're going to check the application that's running into network problems, and see if it's maybe misconfigured, if it's trying to phone home or phone to if it's trying to call out via an incorrect method. And then you're going to check if you're using it right. If there is maybe a problem existing between the monitor and the chair. And that is our network stack. So, woo! Hurrah! That is the OSI model. As promised, we're also going to revisit the difference between TCP and UDP. TCP prioritizes data quality over speed, whereas UDP prioritizes speed of delivery over data quality. Because of this, TCP's emphasis on data quality, it actually guarantees that every single message is going to be received. So in order to do that, it has to establish a connection between the two devices that are talking to each other to ensure that the device that is sending things knows if the stuff is getting received, and to ensure that the person receiving knows that they have received every single message. So they actually establish a connection. And TCP is sometimes called a connection-oriented protocol for this reason. UDP, on the other hand, is connectionless. You just chuck messages into the void and hope that they're arriving at their end destination. TCP, because again, it cares about quality of information, it is going to resend data that the that the destination node says that it didn't get. Whereas UDP doesn't know which packets were received and which ones weren't received, because it doesn't have an established connection. It's, again, just chucking stuff out into the void. And because it doesn't know that, it's not going to resend missed packets. And then finally, TCP ensures packet order. So it ensures that not only is every single bit of data arriving at that endpoint correct and complete, but it's also ensuring that that destination node is reading that information in the correct order, that it's not getting scrambled up at all. UDP, on the other hand, it does have the ability for you to pass along that packet information, but it doesn't enforce using it, and you don't have to have it at all for you to be able to successfully send a UDP message. And that is what we went over in our last session last week. So, any questions, any comments, any concerns before we move right along to IPv4? I'm gonna give a little bit of space and also check on a thing on my other monitor real fast. Because I just realized that I don't actually know what my network connectivity looks like. I don't know if... I like to know the speed at which this is being uploaded to Twitch. It gives me a better sense for how long I should delay. Alrighty. Then we're going to chug on right along to the introduction of IPv4. So, if you recall, we were talking about, with our network stack, you know what? I'm going to exit here again because I want just a copy of the stack easily accessible here. So, as we were talking about in the network layer, there was a protocol introduced called the Internet Protocol. There were actually a couple other protocols, but none of them really got picked up and became a part of what is now the Internet. Where was I going? This is why I shouldn't ever change orders of my slides live in front of people. I get befuddled. So in order for people to know how to send messages to different hosts, you need to have a method of writing an address, right? Just like using the US Postal Service. You need to have a way to... The Information Superhighway Protocol didn't get much traction. Was that an actual name? The one that I always think of off the top of my head is X25, is the protocol I think of. Okay, cool. I was like, that's a ridiculous name, but I wouldn't be shocked if it was real. So you need a method of addressing your envelopes. You need a method of writing down a destination, and you need a method of writing down a source, so that people know where the message was sent from in case they need to say, hey, can you resend that? It got covered in water. So in 1983, the Internet Protocol version 4 was introduced to ARPANET. It actually was first enacted in a network called SATNET back in 1980, I believe. But IPv4 was introduced to the largest network at the time, ARPANET, in 1983. So what is IPv4 and why was it introduced to ARPANET? IPv4 is, you can see it over here, is a particular structure of packet that can be sent over a network. It contains a header and a datagram. So it contains the header that contains all of the information for navigating the network, and then it contains the actual data that you're trying to send over the network in the datagram. And over here, you can see the structure of the IPv4 header. So this first chunk is the header, and then down here is the data. IPv4 is established as a best effort delivery protocol. Your messages that are chucked into the network are not necessarily going to arrive, but the network's going to do its darndest to try to get it to arrive, but it might get lost. Can't guarantee it. If you need it to be guaranteed, you need to be using TCP at the transport layer. Something else has to handle it, not the network layer. IPv4 also supported a number of different methods. So a number of different routing methods, including unicast, broadcast, and multicasting. It did not support any casting. We're going to talk about what those individual things mean in just a little bit. And IPv4 also reserved a number of different address blocks for particular usage. And we'll talk about that in a moment as well. So why did ARPANET switch to a new method of addressing? It clearly had to have a method before 1983 because different devices were able to talk to each other on the network. Different devices were able to talk to each other via ARPANET, right? So the existing protocol that was used by ARPANET prior to 1983, specifically January 1st, 1983, which is also sometimes called Flag Day, was called NCP, Network Communication Protocol. And there are a couple different reasons why ARPANET decided to adopt IPv4. Number one, ARPANET was closely tied to a DARPA project, ARPA and DARPA, right? Was closely tied to a DARPA project that was responsible for the creation of the TCP and the IP protocol, the TCP/IP protocol. ARPANET was also experiencing an increasing number of hosts. So at the beginning of 1981, there were approximately 213 hosts. And there was a new host, a new device, being added to the network every 20 days. And the existing protocol just wasn't going to continue to scale well. Another thing that pushed ARPANET to adopt IPv4 as its networking protocol was the fact that the DoD standardized the use of TCP IP protocol for military in the 1980s. So if ARPANET wanted to still be able to receive DoD resources and have the DoD connected and using ARPANET, and wanted to benefit from any technological advancements that the DoD decided to release, they probably needed to make their way over to using IPv4 eventually. And then finally, two major nodes that were connected to ARPANET, which were NORSAR and University College London, left ARPANET in 1981 to go to SATNET. SATNET was another existing network, large network, and SATNET adopted IPv4 back in 1981. And then NORSAR and University College London decided that they wanted to use the TCP/IP protocol, and since they couldn't do that through ARPANET, they migrated over to SATNET. So all those reasons led to ARPANET switching over to using IPv4 in 1983. So again, just to reiterate, characteristics of IPv4 is that it has a 32-bit address structure. It does best effort delivery. It supports a couple different routing methods. And it has some reserved address blocks for different purposes. So these are some of the reserved, this is a screenshot from IANA, which is the organization responsible for managing all of the IP addresses in the world, and managing the registry of IP addresses in the world. And these are the reserved address blocks. So the most important ones that you're going to see here is this first one, 0.0.0.0/8, which is used for this network. This next one, the 0.0.0.0/32, private use, the loopback, are probably going to be the main big important ones that are worth knowing about as you are like starting to understand how to do networking. But here's the complete list of various addresses that cannot be sold or used commercially because they need to be used for particular purposes to make the internet protocol work, to make sending messages possible over the network. So we've got description, we've got the characteristics of what IPv4 is, what the IPv4 protocol is. We've got why it wound up getting picked up and used. We've got a brief description of some of the special cases, parts that cannot be used, addresses that cannot be used. And now let's talk about the address structure itself, our lovely 16-bit address, our lovely 32-bit address structure. So every IPv4 address is made up of 4 bytes. And you read them in a particular order. That sounds silly to emphasize, but different computers have different orders that they will read information in. Some of them are big endian and some of them are little endian. And so they will read the thing that they will consider the most significant bit, or the most significant byte, on one computer may not be, I'm saying this poorly. Basically, we can talk about the difference between big endian and little endian at some point if y'all are interested in that. it's mostly just a, like, the fact that we have big Indian systems and little Indian systems, so systems that basically format numbers into bytes in opposite order, is just a product of the fact that computers were developed by multiple different people in multiple different places. And does not typically come up as a day-to-day problem for developers these days. But that is why the IPv4 address structure specifies where the most significant bit is because there are some computers that read bytes in the opposite direction, unless told not to. So, IPv4 address structure. We've got the most significant bit over here. So you read the bytes in this order. So 172, then 16, then 254, then 1 in this case. This is the standard way people will write it. Will write the addresses. They'll write it as, often people write IP addresses in decimal notation, not hexadecimal notation. This is what it looks like in bits, in the binary numbers. Yeah, that is what a basic IPv4 address looks like. Now, back at the beginning of when we started using IPv4 addresses, we had a particular method for, so back when we started using this IP address, most routing tables were created manually. And so that meant that we had a particular way of thinking about address spaces, which led to this idea of classful addressing. So back at the beginning of the usage of IPv4, we decided that we were going to have 5 different classes of IP addresses that could be used by different networks of different sizes. And we're going to dive into each one of these, but I want to give a bit of an overview of what that means before we dive into it too much. So basically, to keep things easy for your sysadmins, say your device is connected to a small network that is a Class C network. That means that your network's network ID might be 172.16.254, and then your particular device might be .2 or .12 or .255. And that your network can have at most 256 different devices on your network. So if you are 172.16.254.2 and you want to send a message to a computer that's in a larger network, say 196.4.4, or sorry, say a computer that's inside a larger network, 196.4. And then, specific address for the host within that 196.4 network. Then, given your routing table, if it allows for you to connect to that network, if there is a path to that network, isn't .255 reserved for broadcast? Yes, you are right. Sorry about that. The other thing that's worth noting is here, classful addressing, we don't do this anymore. This was a bad plan. But it's very important to understand because it's why IP addresses are the way that they are. And it's why we ran into this problem where we ran out of IP addresses in the first place. And why we needed to introduce IPv6. So if you are in a Class C network and you want to send a message to a Class A network, your sysadmin can just say, hey, if you have if you're trying to talk to the Class A network that's label is 12, then all I need to do is write 12 star to specify how to get to that node. Yes, we are still failing to properly implement v6. And apparently we may not. There's some discussion about whether or not IPv6 is ever going to be fully implemented. And that is discussion for another time. But yeah, basically, the reason classful addressing seemed like a good idea is because we didn't have very many people connected to the internet at the time. We didn't have a ton of different networks, so it didn't seem like we were going to run out of space. And it made it really easy for your sysadmin to type in just a couple of numbers followed by a star to specify an entire giant network. That's why this happened. So let's go through each of these classes and just give a brief description of them so that you can see how this line of thinking happened. So first up, we've got Class A. So for a Class A network, this is going to be for the biggest networks out there, right? There can be up to 125 Class A networks. And for each of those 125 Class A networks, they could have up to 16,777,214 hosts on their network. Notice a problem here? Up to. But if you give a particular network address, if you give 1 or 124 or whatever to a particular company, to a particular organization, and they don't use all of those host addresses, they don't have 16,770,214 different things connected to their network, they're going to have some wasted IP addresses because nobody else can use those. Because if I am sending a message to 124 and 124 is owned by Evil Corp, wow, my brain exited. If 124 is owned by Evil Corp, if network address 124 is owned by Evil Corp, even if they aren't using host numbers 11 million through 16,777,214, even if they have all of that unused, it's not like Pickles Incorporated can buy that address space from them and use it. Because 124 equals Evil Corp in the registry. Yeah. What the heck? A tale as old as time, Pickles Corp versus Evil Corp. Pickles Incorporated versus Evil Corp. I'm not good at coming up with company names. Okay, so that's Class A. Next, we've got Class B. These are for small to medium-sized networks. There can be up to 16,384 of these networks, And each of these networks can have up to 65,534 hosts. So this might be appropriate for like, just trying to think of a company. No companies anymore. This might be appropriate for, like a regional burger chain, theoretically. They're probably not going to have more than 65,000 computers, right? Next up, we've got Class C. There can be up to 20,000, up to 2,097,152 Class C networks. And these are going to be networks that are quite small. This is going to be like a single office building, maybe a fancy house that has a lot of connected devices, maybe a school. Is going to be a Class C network. Because you can only have up to 254 devices sitting on that network. Then we've got Class D. This is a special chunk of the internet that is reserved exclusively for a special chunk of internet IP addresses that was reserved exclusively for multicasting. Now, multicasting, I am going to go ahead and jump ahead. Multicasting is the ability for one device to send to multiple other devices that are saying, hey, you can send to me. I will take your thing and pass it along. So Class D IP addresses are reserved for that particular use case, that particular style of networking. By and large, the internet functions via unicasting, which is I am a single host. I am going to send to I am a single node. I am going to send my message along to another single node. But multicasting is sometimes helpful. We'll talk a bit about under what circumstances multicasting tends to be used. But it is not the predominant method that people send out information, but we thought it was going to be more useful than it wound up being. Yes, mesh relies on multicast, though we have not covered mesh networks yet. And then finally, Class E. This is reserved. This is just reserved for research purposes. Weird shit we might want to do in the future. This was just, hey, we might need a chunk of hosts, so we're gonna just say you can't use those yet. So here's our summary. To just quickly reiterate, we've got Class A is big networks, Class B is small to medium networks, and Class C is pretty little networks, probably your house or your street. Class D is for special use case for your mesh networks. And Class E was for future research weird shit. However, as we said, there's a lot of waste. What if Evil Corp doesn't use its entire address space? What if What if Pickles Incorporated starts later in the game and all of the IP addresses in their class size, Class C, have been bought up? How are they going to get address space? How are they going to be able to connect to the internet? And we first start talking about this problem in June of 1992 is the first time this gets described and discussed. And the IANA, which is the entity that oversees all of the IP addresses, actually releases this memo and this discussion called RFC 1338, which, as you can see here, discusses strategies for address assignment of the existing IP address space with a view to conserve the address space and stem the explosive growth of routing tables in default route-free routers run by transit routing domain providers. Yeah, the concept of the modern scale of the internet was not considered when IPv4 was decided upon. As you can see, we have the establishment of the first commercial ISP in 1989, and we get a bunch of shit connecting to the internet in that period. And we start to see, oh wait, more devices might wind up on this network than we thought. And that is when people start talking about it. Then, and in fact, we have run out of addresses. Even with some of the changes that we've made, for example, abandoning classful IP addressing for some more efficient methods, we still ran out of address space. The very last chunk of free address space in Class C was used back in January of 2011. What if Donut Heavy Industries LLC comes along and can't get a public block of addresses? Exactly. And in fact, they can't now, right? We're out of them. We are out of space. Okay. So when we first started getting the inkling of, hey, we might run out of space, there was this new thing that was created and introduced called CIDR. And CIDR is classless interdomain routing. This was meant to solve that problem of Evil Corp having a lot of their address space that they're not using. So rather than doing your routing based on network ID like this and just having 125 star after it in your routing table, what if instead we kind of abandon the idea of classes and we just look at network prefixes? And this introduced a new style of notation. And this is how you will see most IP addresses written today, using this CIDR notation. So first up, if you are going to be able to use varying lengths of network prefix, you need to be able to specify how long that network prefix is, because we no longer have those classes that mandate a particular size for the network ID, right? For the network prefix. We're no longer guaranteed to have 8 bits, 16 bits, or 24 bits of network specification. So now we have the ability to specify the length of the network prefix. And that's done via this slash here. So 24 bytes or 24 bits, that means that this chunk here must be the length of the network prefix. And then anything after that is the identifier of your individual host. So the individual thing, the individual device connected to your network. Yes, analog, that's another great example. 10.0.1.1/16. So what that's saying is that first chunk, the first 16 bits, so the first 2 bytes, 10.0, that is my network. And then my individual host is that 1.1 part. And this was introduced and widely adopted in 1993. In 1993, IANA switches over to using this method of distributing IP address blocks. And now we get to the part where I ran out of time to create slides. Yes, an analog is correct. We simplify out the zeros for human legibility purposes. So now we're going to start talking about the different kinds of routing. And I'm going to do just a brief overview of the various categories of routing that we have available to us before calling it a day. Because I feel like quite a bit of information there in the IPv4 stuff and the history of how we got from 1983 and the introduction of IPv4 in ARPANET to the introduction of a new method of network addressing and tracking networks with CIDR. So in routing, we have 4 different major kinds of methods that networks can use to do routing. You can have unicast, which, as I said, is what most of the communication on the internet uses, where if you are trying to send a message to get to a particular destination, you are going to pick from the various different nodes that you are personally connected to. You're going to pick from these various nodes, find the one that's best, maybe shortest distance, and send your message there. So one-to-one. I have a message that I want to throw into the network. I'm going to send it to the node that says it's the shortest distance away from the node that I want to send it to. That's unicast. Broadcast. You want to send a message to a node. Rather than doing anything to limit the number of messages that you are sending into the network, maybe what you're going to do instead is just pass it along to everybody. This is like if you have someone that you want to get in contact with, say Fiona, and you don't have Fiona's phone number or her address or any way of getting directly in contact with her, and you don't necessarily know anyone else who does either. Or you know that a couple of your friends probably have contacts with Fiona, but you don't know who's going to get it there fast enough, and you want to make sure it gets there as fast as possible. You can broadcast. So you can give your message intended for Fiona to all of your friends, everybody you know, and say, hey, can you pass this along to Fiona? And it'll hopefully eventually get to Fiona. Broadcast is a very selfish method because once Fiona gets the message to her the first time, she doesn't need the rest of those copies, but they're still going to be taking up bandwidth within the network, right? They're still going to keep trying to make it to Fiona until they get there. And so they can create a lot of noise and what's the word I'm thinking of? Congestion, there we go. Can create a lot of congestion in the network. Next up, we've got multicast. Multicast is kind of similar to broadcasting, but it's a little less noisy. So multicast is where you have your message and you want to get it to Fiona. And so you look at your list of friends who have said that you look at your list of people that you're connected to, and next to each of your friends, you have a little, give me 1 second, somebody is here at my house, and I was not expecting that. So I'll be back momentarily. Hello, lovely people. I am back. So multicast is similar to broadcast in that you're still sending it out to a bunch of people and maybe creating some more congestion in the network, but you're not sending it out to everybody you know. You're only sending it to people who have said, yeah, I'll pass along messages to Fiona. So limited blast. And then Anycast is kind of a mixture of multicast and unicast. What you're going to do is you're going to look at your friends who have said, yeah, I'm willing to pass along messages to Fiona, and you're going to pick one of them. And that's roughly how Anycast works. We're going to go into a bit more detail on those particular methods in the next couple of days. But yeah, that's basically where we're starting. Unfortunately, I think I need to actually go handle a bit more things. For those who have been following along with the rat journey, we have rats, which we've been trying to get rid of, and they keep finding new ways into the house. So I need to go talk to the inspector who is collecting rats. But I will be back with you tomorrow with more discussions of unicasting, multicasting, broadcasting, anycasting, and we're going to get into the development from static routing into dynamic routing. So, which is basically sysadmins got sick of maintaining really, really long routing tables as more and more devices got added to the network. So keep your eyes tuned for that. I'll be uploading these slides. And as always, my YouTube video, I'm uploading all of these to YouTube. So if you don't follow me there, go ahead and drop me a follow. It helps, helps the algorithms. And you'll be able to review these VODs at any point in time if you want to review particular aspects of the network stack discussions. So see y'all tomorrow. We're also going to be talking about some of the various different kinds of cyber attacks that can happen due to routing techniques, and why, again, we abandon certain methods of routing algorithms because of their susceptibility to particular kinds of attack, like Smurf attacks. So tune in for that, and I'll see y'all tomorrow.